Okay, in this lesson we're going to look at some of the basic rules of probability. So first, some definitions. So we're going to talk about an experiment. This is a controlled operation that yields some set of results. And the possible results of an experiment are called its outcomes. An event is a subcollection of these outcomes of the experiment. And then the sample space is if we could list out all the possible outcomes, that would be the sample space. Sometimes you can't do this, but other times you can, and we'll look at some examples of these. So here's like an example of an experiment. Experiment could be you roll a die, and an event of that is you roll a 3. And then the sample space of rolling one die would be a list of all the outcomes. So here's a list of anything that can happen, right, on a regular 6-sided die. I can get a 1, a 2, 3, 4, 5, or 6. Similar, another experiment could be you pick a card. The event could be you select a king. Maybe you want to find the probability you select a king. And so that's the event. That's selecting a king. And the sample space would be 2 of hearts, clubs, spades, diamonds, 3 of hearts, spades, clubs, spades, diamonds, ace, and so forth, all the way to ace. Another last experiment we're looking at, tossing a coin. So the event could be you get a head. So the sample space, you toss a coin one time, is just head or tail. So we all have sort of intuitive sense of probability. Sometimes this is wrong, though. So I want to go back to just the intuition of probability and see if we can somehow quantify that and to be able to work some of these problems. So define the probability of an event, and that event is E. The probability of E, the number of ways E can occur divided by the total number in the sample space, the total number of possible outcomes. And the assumption here is that all events are equally likely, like when we roll a die. Okay, so let's find the probability of rolling a 3 on one roll of one die. So again, our formula, the number of ways we can roll a 3 divided by the total number. So how many ways can I roll a 3? Well, there's one way to roll a 3. So my probability would be 1 divided by the total number of outcomes. Now for this one, let's list it out. What can I possibly get when doing this? I can get a 1, 2, 3, 4, 5, or 6. And so there are 6 possible outcomes. So my probability is 1/6. And there it is. Another example, find the probability of selecting a king with one draw from a deck of cards. Again, if you'll go back to this notion of the number of ways it can occur divided by the total, it'll really help your thinking. Sometimes these problems get very complicated, but if you come back to this notion of a basic probability, you're often able to determine these probabilities. So we have to ask a question, how many ways can I select a king? So how many kings are in a deck? There are 4 kings in a deck. Divided by the total number in my sample space. How many cards are there in an ordinary deck? 52. And then we can reduce that to 1/13. And you can even write that as a decimal if you want. Okay, flip a coin 2 times. Let's find the probability of obtaining, and then we're going to have 4 different problems. And it may be helpful if we list out our sample space first. So what can happen? I'll list it up here. So one thing that can happen is I can get a head on the first toss, and then a head on the second toss. And I'll represent that with HH. That should make sense. What else could happen? I could get a head on the first toss and a tail in the second one. But I could also get a tail in the first toss and a head, and then I could get 2 tails. So the part that confuses some students is you got to list both of these outcomes here. The fact that it can occur on the first toss, the head can be on the first toss or the second toss. Okay, so exactly 1 head. So how many of our outcomes have exactly 1 head? We'll call this sample space S here. We have 2. So our probability is going to be 2 divided by the total number in my sample space, which is 4. So we get 1/2. So again, what this means is that in the long run, if we flip this coin 5 1,000 times, roughly half of those, sorry, if we flip coin 2 times, we do we flip 2 times, and then we do that 1,000 times, half of those two flips are going to contain 1 head, exactly 1 head. Okay, how about exactly 2 heads? Exactly 2 heads is right here. And how many times does that occur? 1 time divided by the total number, which is 4. What about exactly 3 heads? Well, there aren't any. So if the probability, if it cannot occur, the probability is just going to be 0. If we say at least 2 heads, well, let's change this. Let's make this at least 1 head. Because at least 2 heads is the same thing as 2 heads, because we can't have 3 heads. Let's say at least 1 head. So at least 1 head would mean what? 1 or more. So it would actually include all 3 of these right here. So there are 3 successful outcomes divided by the total of 4. So we've kind of encountered one of these rules here that the probability is always between 0 and 1. So if it's certain to occur, we say it's 1. Sometimes if we convert this to a percent, we'll say 100%. If it cannot occur, and I think this makes sense, it's 0. And something we'll look at a little bit later, the sum of all the probabilities for the sample space is 1. If I found, back in example 4, if I found the probabilities for each one of these and I add those up, I need to get 1. So if I found 2 heads, 1 head, and 2 tails, add those up, I should get 1. Okay, there's also empirical probability. So given some sort of frequency distribution, the probability of the event is given by, and then the frequency of that class divided by the total frequency distribution. And this will make sense once we see an example. So a pharmaceutical company is testing a new drug supposed to help with weight reduction. So the drug is given to 500 people. And here are the outcomes. It reduced weight in 279 of them. It was unchanged in 92, and it actually increased to 129. So if it's given to an individual, what's the empirical probability the person's weight is reduced? So that's our class, the reduced weight. So we take the number in that class, 279, divided by the total number, 500. And we will often write these in decimals, so we'll go ahead and do that. So 279 divided by 500. So about 0.558. You could say 55.8% if you wanted to write as a percent. Okay, let's move this calculator down. Okay, the last 30 birds that fed at the bird feeder were 15 robins, 10 blue jays, 8 hummingbirds. That doesn't seem right. This doesn't add up to 30, does it? So let's just make this 5. Okay, so 15 robins, 10 blue jays, and 5 hummingbirds. Use this information to determine the empirical probability that the next bird to feed from the feeder is a blue jay. So, how many blue jays do we have? We had 10 divided by the total number of 30. So we get 1/3, which is about 0.33. Okay, so law of large numbers. So when a procedure is repeated a large number of times, it will actually begin to approach the actual probability. So let me show you a little applet with this. So it's the long run relative frequency. So here I've got a simulation here. I'm going to roll a dice, 1 die, and let's roll it 1,000 times. Let me show you 1 time so you can see. So I roll it 1 time, I get a 1, I may get a 6, I may get a 2, another 1, and so on. So let's roll this a bunch of times. Let's do it 1,000 times. And this is kind of what we'd expect. You know, these are equally likely. We can see there's some variation. If I rolled it another 1,000 times, notice that we are slowly getting closer to a flat line here. The more I roll this dice. In fact, I can bump it up to 10,000. You notice how all of this goes really close together. So the more I do an experiment, the closer it gets to the theoretical probability. Okay, here's another example where I've tossed a coin here 10 times. I get 5 heads, which is about 40%. And we know the probability of getting a head on a toss of a coin is 1/2. We have 2 choices, a head or a tail. And notice our probabilities, as I increase the number of tosses, it actually gets closer and closer to the theoretical probability of 1/2. That's really important. That's one of the biggest things I want you to get out of the probability lesson. As I increase the frequency, the number of tosses in this case, the closer I would expect to get my relative frequency to be closer to the theoretical. So the addition rule. So if I have to determine the probability of a compound event, we're looking for event A occurring or event B occurring, we want to find the total without double counting. We don't want to count them twice. See what I mean? So the probability of rolling a 2 or a 3 with one roll of one die. A 2 or a 3, it's just going to be the probability of a 2 plus the probability of a 3. 1/3. Hopefully that makes sense. So we have a formula. If I had the probability of A or B, and sometimes we'll use the union symbol here to represent that, it's simply the probability of A plus the probability of B. It's formula 1. There will be another one here in a moment. Let's look at this example. So a single card is drawn from a deck of cards. Find the probability of selecting a 6 or a club. So I've given you the sample space down here. So a 6 is this one right here, right? So if I'm going to use my formula, the probability of a 6 would be 4 over 52 plus a club. Where are my clubs? Right here. And how many clubs do I have? I have 13 clubs, but if I add 13 here, what have I done? What's wrong with the way I've written this? I'm double counting this 6 of clubs. I'm counting it twice. So I have to subtract it out. I have to subtract out one of them. Okay? Or, in an example like this, you can subtract it out before. You could say 4 over 52 plus, and just go ahead and say 12 over 52. But it's not always that easy to see. So when the events can actually occur at the same time, we have to subtract it out. We don't want to double count, as I mentioned earlier. Add them together in a way that we don't double count. And the visual formula for that looks like this. So the probability of A or B is A plus B minus the intersection, minus the probability of A and B. So if they cannot occur together, like with the dice problem, when we were rolling a 2 or a 3, we can't get a 2 and a 3, we didn't have to worry about that. Those events are called mutually exclusive. And you may have heard that word used in other contexts, when things cannot happen at the same time. And here's a Venn diagram to illustrate that. When they can happen at the same time, I have to subtract that intersection. So let's play around with this for a second. Let's make sure we're able to determine events that are and are not mutually exclusive. So we roll a die, get an even number, get a number less than 3. Are those mutually exclusive? Go ahead and pause the video here and see if you can get these, and I'll be back in a second. Okay, welcome back. So these events here, getting an even number. So even numbers are what? 2, 4, 6. And then numbers less than 3 would be 1 or 2. I see this event here, this outcome here occurs twice, so these are not mutually exclusive. Roll a die, get a 4 and a 5. You can't get a 4 and a 5. So these events are mutually exclusive. You pick a card from a deck of cards, get a jack, and getting a king. You can't get a jack and a king, so these are mutually exclusive. But as we saw earlier, pick a card from a deck, you get a jack or a black card. You can get these at the same time, so these are not mutually exclusive. They will have an intersection. There are 2 black jacks. Okay, so now let's look at some probabilities. You get a jack or a king. So in some of these, you're going to use the formula where we have to subtract out the intersection, and some of these you're not. Pause the video here, see if you can do these. All right, welcome back. So the probability of getting a jack or a king, there are 4 jacks plus 4 kings. And often when I'm doing these, I'll work in this way, and then I'll ask the question, can I get a jack and a king? No. So I don't have to worry about subtracting the intersection. I'll get 8 over 52, and we'll reduce this. 4 goes in both of those, so 2/13. And you can put that as a decimal if you want. So to get a jack or a black card, we're going to have 4 jacks minus, how many black cards do we have? We actually have 26. We have 13 clubs and 13 spades. Both of those are black. But then I need to subtract out the black and the jack. Black cards and jack cards, and there are 2 black jacks. Okay, and add those up, so I'll have, sorry, that should be a plus. My plus didn't come through. So 4 plus 26 would be 30, minus 2 would be 28. And then I'll let you reduce that. Well, let's see, 4 goes into 28 7 times over 13. And we would expect that a little more than half, right? Because half would be black cards, and then we add a jack to it. So always look at your answers to make sure they kind of make sense in the end. A club or a spade. So how many clubs do we have? So we have 13 clubs plus 13 spades. Can I get a club and a spade? Nope, don't need to worry about that. This is half. These are the black cards. How about an ace or a club? So there are 4 aces plus. Now here, let me show you something you can do. Clubs, you've got 13 clubs, but one of those is an ace. You can just go ahead and subtract that in your head. And you get 16 over 52. Which reduces to 4/13. You don't have to do it that way. You could have done plus 13 over 52 minus 1 over 52. Very similar to what we did with part B. Okay, this is a good little problem. So these are the types of problems you'll probably encounter if you're going to encounter probability in your job setting, where you have some sort of table and you want to know how likely something is to occur. So we have a guidance counselor at a middle school collected the following information regarding employment. So we have the number of children under 18, 0, 1, or 2 or more, and then worked. So husband only, wife only, and both spouses worked. And then we're going to have some questions associated with that. So here are our questions. So what's the probability that for a married couple selected at random that both spouses work? And I'll let you read the other ones on your own. So I'd like you to pause the video and see if you can work through these before you watch me do it. Okay, so here's part A. What is the probability that for a married couple selected at random, both spouses work? So again, go back to, we want to count the number of people that fit that class, both spouses working. So we have right here, both spouses work, 1149. And divide that by the total number, 1700. So our intuition sort of pays off on many of these problems. So we're going to have 1149 divided by 1700. We almost always will convert these to decimals when we have big numbers. Because this, I have a hard time conceptualizing what that means, but 0.675. Well, some are probably 675, 676 if we want to round correctly to 3 decimal places. I don't like that. 0.676. Or you could write this as a percent sometimes, 67.6%. If you are taking a course with my math lab, it'll tell you how to input the answer and what to round to. Okay, part B. What is the probability that for a married couple selected at random, the couple has 1 child under the age of 18? pause the video here. If you have not done that yet, pause it. I know you can do these on your own without watching me. All right, welcome back. So the probability that for a married couple selected at random, the couple has one child under the age of 18. So we count the number that are in that class. This one right here, 353, meet that condition, divided by the total of 1,700. And then we're going to pop that into the calculator and get a decimal. 353 divided by 1,700. Sometimes I use little wavy lines to approximately equal to 0.208, or about 20.8%. Okay, part C. What is the probability that for a married couple selected at random, the couple has 2 or more children under the age of 18 and both spouses work? So 2 or more children under the age of 18 and then also both spouses work. Okay, so again, we're looking for that class. So here's 2 or more, and here's both spouses working. So how many fit that criteria? Right here. This is where those two intersect, right? So we have 370 divided by the total of 1,700. $370 divided by 1,700. 0.218. Okay, part D. What is the probability that for a married couple selected at random, the couple has no children or only the husband works? Okay, so let's think about this. So has no children or only the husband works? Okay, so we need to add this up, right? So we're going to have, we have a total of 788 where nobody worked. Or sorry, where has no children. So 0 children, 788 out of the 1,700, plus, or the husband works, which is 425, divided by 1,700. But what have I done if I add those up? I've double counted this 172. The husband only worked with 0 children, so I've got to subtract out one of those. So I've counted that twice. We can use our calculator here. So 788 plus 425 minus 172. So we have 1041 over 1,700. And we get 0.612. So the last one here, would it be unusual to select a married couple at random for which only the wife works? So this unusualness quality, remember we're looking at if this is less than about 0.05, then we call that unusual. Less than 5%, 5 out of 1,000 times, we say that's pretty unusual. So would it be unusual to select a married couple at random for which only the wife works? Okay, so only the wife works is 94 divided by 1,700. So let's find out what that decimal equivalent is. 94 divided by 1700. 0.055. So this is not less than 5%, 0.05. So we would say no, we would not consider that unusual. It's pretty close though, but we have to have a cutoff somewhere. For this text that we're currently using, 0.05 is that cutoff, and we'll kind of see why in subsequent lessons. We could say, would it be unusual to select a married the wife only worked with two or more children, and that would be yes, because that would be 15 over 1700, which is definitely less than 0.05.